This is the usual story. Shut your laptops, you know. And today, for once, I'll say, wear your costumes. I have some here for you. Please return them after class. But after class, we have like a 5-minute window. We will all come up here and take a group picture. It's tradition. You have to look your, beautiful best, right? And so let me begin. We're going to sort of continue our series of lectures on recurrent models. But specifically, the kind of models we are going to be looking at are sequence-to-sequence models. So here's the kind of problem we've been looking at, whether you realize it or not, which is a sequence goes in, x1 through xn, and some other sequence comes out, y1 through ym, where the number of symbols in the output need not necessarily be the number of symbols in the input, number of elements in the input. So we saw an example, speech recognition, speech goes in, a word sequence comes out, other things like machine translation. One word sequence goes in, another word sequence comes out. Dialogue, a user's input goes in, the system's response comes out. Or question answering, a question goes in, a response comes out. All of these are just sequence-to-sequence models, right? A sequence of inputs goes in, and the output is also a sequence. And in general, there's no need for any kind of correspondence between the input and the output. There are a couple of variants that we can identify immediately. The first one is something we've dealt with already, which is the one on top, where the input and output are not the same length, but there is an order correspondence, meaning the first portion of the input corresponds to the first symbol coming out. The second portion of the input corresponds to the second symbol coming out, and so on. The one that we are interested in today and in the next class is the second one, where there is no, there may be no correspondence whatsoever between what goes in and what comes out. Here is an example from machine translation. I ate an apple. A somewhat poor German translation is Ich habe einen Apfel gegessen. So now, if I translate it so, then, and I chose this particular example simply because it illustrates a few points. Asia and I can be mapped onto one another. But the 8 on the left side actually became habe and gegessen, which are two words separated far apart, right? And so similarly, and is einen Apfel. So, but you can see that there is no correspondence, one-to-one correspondence. And in fact, it can be much worse. If this were a dialogue system, the input would be, my computer is frozen. And the response must be, do you have a blue screen, right? Absolutely no relationship between what goes in and what comes out. So where did I keep my clicker? Here. How do we deal with problems of this kind? So here we have a situation where the input and output may have no correspondence, right? And so that's what we deal with. But before we even get there, we're going to spend 10 or 15 minutes, maybe a little longer, looking at a somewhat different problem, which is, language generation. Now here, for example, this is from an open source project. Does anybody recognize this? What does it look like? I won't expect you to recognize it simply because it's completely, fake. So this was a very simple LSTM model, I think 3 layers of LSTMs, which was trained off Linux source code and then just used in generative mode, and it outputs completely valid Linux code. Now, we're not speaking of the fancy ChatGPT kind of system. We're literally speaking of a few layers of LSTMs. And look at how good it is, right? It's actually managed to open and close braces, open and close parentheses. The variables are correctly closed off. Within a parenthesis, the correct variable is actually being incremented. It knows what to do. Part of this, of course, is due to the fact that if you're using an LSTM, LSTMs have this ability to remember things for very long periods of time. But more important and much more impressive is the fact that something that's so simple could generate data of this kind, and it's completely imaginary and random, right? Or here's here are more examples, right? This one is, this one was trained off Wikipedia. Again, just a few layers of LSTMs. And as you can see, it's actually managed to capture the structure of these Wikipedia pages well enough that it is generating something that looks completely authentically Wikipedia. Those square braces, those are links in Wikipedia, right? Or so all of these are simple recurrent networks. I picked the examples of Andrei Karpathy's GitHub page, where he has a very nice page on the unreasonable effectiveness of recurrent neural networks. These days, of course, we aren't necessarily speaking of recurrent neural networks. We're speaking of transformer models and such like, but it all begins here, right? So, but what are we doing in all of these examples over here? What we are doing is to model language. And one that you're all familiar with is ChatGPT, GPT-4, Bard, all of them, right? They're all modeling language. And so we're going to spend some time looking at modeling language using recurrent networks and more generally modeling language, right? And embeddings. So language models model the probability distribution of token sequences in the language. We're not specifying what the token sequence is. It could be sequences of characters. It could be sequences of words, of something more complex, of numbers, any odd symbol. It doesn't matter. It's just that you have language, which is a sequence. And language, as it is presented to you, is sequential, right? So you get sequences of symbols. And language models model these sequences. And they can also be used to compute the probability of a given token sequence. So I give you a token sequence. I say, how probable is this token sequence in this language? And a language model must, in principle, be able to give you this answer. And the flip bit, you should be able to say, just give me a random token sequence from the language, and it should be able to generate a highly probable, you should be able to sample a highly probable token sequence from the language using the language model. So what do they look like? The actual target of a language model is always, always, always to model the probability distribution of entire token sequences. So here, for example, if I've got W1, W2, W3, W4, this is a token sequence, right? And this is an end-to-end sequence, a complete, and how I define the sequence is up to me. I could be thinking of sentences. I could be thinking of paragraphs, entire passages, an entire book. It doesn't matter. The point is, eventually, that's just one sequence from a language. And the job of the language model is to tell me how probable it is. But more generally, the job of the language model is to model this probability distribution. What do I mean by modeling the distribution? Again, it means it's some mechanism where if I trigger it and randomly pull something out, it's more likely to get, it will produce token sequences where it's more likely to produce token sequences that are more likely in the language and less likely to generate stuff which are less likely in the language. So that's capturing the distribution itself. And on the other side, given a sequence, it should be able to tell you how probable it is. But the problem with trying to model something of this kind is that, how many token sequences are there in the language? Infinite, right? So we can't just say, feed me a token sequence and I'll give you the probability. Modeling that is very tedious. So the way we do it is to do it in an incremental manner. And we're going to use Bayes' rule for it. So the target objective here still is this one here, right? The word sequence, the probability of the word sequence. But if using Bayes' rule, I can say this is the probability of the first word times the probability of the second word given the first word times the probability of the third word given the first two words times the probability of the fourth word given the first three words and so on, right? So we can sort of make it incremental where at each step you're simply predicting or computing the probability of the next symbol in the sequence. And so in so doing, they actually end up being characterized as next symbol predictors. Now again, language models are built as next symbol predictors, but what they are really doing is modeling the probability of the entire token sequence, right? And so here's how you would set it up. You'd be setting it up through next word prediction if you were doing words. And if I were using recurrent neural networks, I'd be doing this using recurrent neural networks. Now, again, this is a series of lectures on recurrent neural networks, so that's what we're going to assume we're using right now. So here's the thing. Four score and 7 years. What is the next word? At least the Americans here should be able to tell me, right? Go. Is the word ago, right? So how did you know that?
Common from Lincoln's address.
So in that context, that is the word that happens most frequently, right? Nobody ever said 4 score and 7 years apple. It just doesn't happen in real life. And so we are really characterizing what Joshua just did was to tell us what the most frequently occurring word was in that context. He modeled the next word. If I gave you this next sequence of characters, A, B, R, A, H, A, M, L, I, N, C, O, L, what is the next character? Obvious, right? It was obvious to you. So when I'm speaking of building a language model, when I'm speaking of building a neural network to do the next word prediction, next token prediction, I want a network which can do what Josh just did, or what Maukhik just did in the second example, right? So to do this, first, of course, language models, and we're going to use recurrent neural networks. These are mathematical machines. They're not going to deal with words. So the words have to be converted to some numeric format, and we're going to use our well-known one-hot representation for it, where I would have to pre-specify my vocabulary. Here are all the words that can occur in my language. And then I'd have to arrange them in some alphabetic or some pre-specified order, maybe the dictionary order. And then every single word in the language is simply going to become a one-hot vector, which is a vector with as many components as the number of words in the dictionary, and a 1 in the location of the specific word itself, right? And similarly, if you were building a model for characters, they can be similarly represented. You'd have, if you were building a language model for words in Russian. Now, in order to survive in Russian, you need a vocabulary of about 400,000 words. So your one-hot vector is going to be 400,000 dimensional, of which 39999 are going to be 9 are going to be zeros, and one of them is going to be 1, right? Whereas if you were building a character language model, then if you're doing this in English, you need about 100 characters all told, including numbers, lowercase, uppercase, all the special symbols. And so the vector would be a 100-component vector, of which 99 would be 0. And the 1 would correspond to the index of the character in question, where you have pre-specified the order in which the characters must be considered. Right? And so now, when I'm building a language model whose job is next token prediction, what I really want is a function of this kind, which takes in maybe the first n words or the first n tokens, and outputs the n plus 1th token, right? So it's going to take in W0 through Wn minus 1 and output Wn. So if I were to draw it differently, since everything is going to be represented as one-hot vectors, I'm going to have n one-hot vectors corresponding to the first n tokens in my sequence. It goes to my function, whatever the function might be. And the output is also going to be a one-hot vector, which represents the next token in the sequence. So far, so good. Here's a problem. Going back to my example of Russian. My vectors are all, if I have 400,000 words in my vocabulary, how large would my vectors be? 400,000 dimensions, right? The dimensionality is huge. You're looking at a very large dimensionality for the input. And correspondingly, you're going to need those many parameters. Do we really need those many parameters? And learning all of those is going to be a pain, right? You don't want to be dealing with high-dimensional data. But there's something even worse about one-hot vectors, which is that one-hot vectors are incredibly wasteful of space. So every time I add a new vocabulary word, I'm adding an entire new dimension to my space, right? When I do so, now think about it. What is the total volume occupied by all of your training data in this massive space? Yeah, but the volume is 0, right? Because each training data point is exactly 0 volume. Whereas your space has infinite volume, or even if you bound it and say everything must lie between 0 and 1, the space might have unit volume. Your data is occupying 0 volume of it, right? You have nothing, if you think about it that way, right? And so even if you're thinking of it in terms of density, number of training data points per unit volume, the volume, as you increase the number of data training, the size of your vocabulary, the number of elements in the vocabulary increases linearly. The size, the volume of the space that you're stuffing them into increases exponentially, right? With the number of words. And so as you increase the vocabulary size, the density of tokens per unit volume in your space falls so fast that you're basically not using the space at all. So this is a terrible thing for us to be doing. And that's one. The second is that there's no semantic meaning to it, right? So here, if I had a vocabulary of only 3 words, the only 3 vectors that are possible are 0, 1, 0, 1, 0, 0, and 1, 0, 1, and 0, 0, 1, right? The rest of them are not valid vectors. So if I gave you something like 1 epsilon 0, where epsilon was 10 raised to minus 21, would that mean anything? It has absolutely no meaning whatsoever, right? So basically, even the space, even if you're willing to accept the exponential collapse in the density of points with the increasing volume, the fact that once you have even a small perturbation from the exact points that you've got means nothing, makes it problematic, right? So we can't actually deal with all of these, but still, given that situation, this is the horrible situation we find ourselves in, why do we use one-hot vectors? Can you think of any other way of representing words? Anybody? Yeah. So I'm not giving you the option of embedding, right? That's already a transformation. I'm just saying, a priori, how would you do it? Can you think of any other way? Integers? Perfect, right? But then how's an integer different from a one-hot vector?
Integer is only in 1D space.
When I represent it, what's it going to be, right? Any other things? If I were to choose binary, for instance. Yeah? Takes basically, I can take any, if I have a vocabulary of n words, I can take any log n sequence of binary numbers, right? I just need log n bits. So with 3 bits, I can represent up to 8 words. With 4 bits, I can represent up to 16 words. I can just assign different bit combinations. So I can still be using the same cube, but I could be assigning words to every corner of the cube. Could I not? And I'd be doing a much more efficient usage of the space. Why don't I do that? Yeah.
That's kind of like deciding on the.
That's exactly it. So we do not want to assign any meaning to the position of the word, nor do we want to assign any meaning to the distance between words. What is the distance between any 2 words over here? 1? Square root of 2, right? The distance between, so basically you're not biasing yourself a priori onto any kind of relationship. You're not saying these two words are closer and these two words are farther because we don't know. I mean, it's English, so maybe you can make some interpretation. If I were working off characters, is E closer to Z or is it closer to A? How do we know? We don't, right? And so we decide that we're going to be agnostic to that. And our initial representation is indicative of our agnosticism to the relationship between words. On the other hand, it ends up being extremely wasteful. And so what we want to do is maybe reduce the dimensionality. That's where the embedding business comes in, right? You want to go from this high dimensional space and you want to lower the dimensionality. And what is this business of lowering dimensionality? You're going to say, I will project all of my data points onto some plane. And this would be a lower dimensional plane. In my 3D example, where I have 3 words, I find a 2-dimensional plane, and I project all of my data points onto this 2-dimensional plane. Now, what is this business of projection? Projection is a linear operation, right? You have a projection operator P, it's a matrix, and you multiply your original vector with P, and it's going to give you a point on the corresponding point on this lower dimensional space. And so the thing is that once I project the data down, I'm reducing the dimensionality of the space. And although it doesn't solve all of our problems, it does say that I can bring the density of points per unit volume. I can increase the density of points per unit volume. And second, if my projection P is properly learned, then the distance between words might just make sense. And so the whole idea is we want to bring this data up from the high dimensional space down to a lower dimensional space. And we want to do so to improve the density. And we want to do so in a manner such that the distance between points actually makes sense. And now, this projection is just an operator P, right? Which means that I can take every vector, W, multiply it by P, and now I get the projected version going in. And observe how I would do this. I'm going to be projecting things going into the function because I'll be looking at the lower dimensional data going in. The prediction is not a projection. The prediction is still the actual word itself. So the output is still 1 hot. What goes in is the projected version. Now, the same projection applies to all the words. The projection is a matrix, right? So in neural network terms, what is a projection?
Layer.
What kind of layer? It's just going to be a linear layer, right? So that's like saying I have a linear layer following every one of these words, except every one of these linear layers is exactly the same. So alternately saying, I can view this as a network which has several subnets that are identical. In other words, a shared parameter network, right? So now if I want to learn my language model, I can learn my language model in a bunch of different ways. I can have a recurrent network which says I'm predicting the next word based on everything I've seen in the past. Or I can have something simpler which says I'm predicting the next word based on the past k words. So the predicting the next word based on the past k words is a k-gram network. That's what it's called. And that would be something like this, right? Each word, in order to predict each word, you're looking at the past several words. And so what kind of network is this? It's a 1D CNN, right? A convolutional network. And it will be predicting the next word, except, of course, that when you're performing the prediction out here, you're going to have the P at each point, right? The projection operation, the linear layer which projects the 1 hot vector down to the projected lower dimensional representation. So and of course, now how you can train this model in a very simply, you can always train it to predict the next word. We'll take a look at that. But then for the longest time, simply this act of learning this projection which brought these vectors down to a lower dimensional space, ended up being considered very important. It still is. Because it turns out that learning the appropriate representations for words can make life very simple for us. You get semantically useful mathematical characterizations for words. And so there are other possibilities, like trying to predict a word based on all the words on either side. This was called a soft bag of words. So to predict any word, you'd be looking at the k words preceding it and the k words after it, and you'd be predicting the word in the middle. Or you could be using a word to predict everything on either side. That's a skipgram. You'd be in this example of mine. I'm using the 7th word in a sequence to predict words number 1, 2, 3, and actually no, 4, 5, 6, and 8, 9, 10, right? 3 words on either side. So regardless of how you did it, you can actually learn the model to perform these operations. And again, the key here is that there's a projection operator, which is projecting the word down. And once you project the word down, there was this famous paper back, this is 2013 by Mikolov et al., where they showed that if you learn these projections properly, you end up capturing some very interesting relationships between words. So these are actually the actual word projections were hundreds of dimensions. They use PCA to get 2-dimensional visualizations. But then what you see over here is the vector that connects China to Beijing ends up being more or less the same vector that connects Russia to Moscow and Japan to Tokyo. So it has managed to capture the notion of capital of in the representation. They have other examples where they show that king minus queen is the same as man minus woman. Now, given that these are all cherry-picked examples, the fact that this happens for even a subset of the vocabulary is pretty astonishing, right? That all we did was to impose a projection on the data and then learn to predict either the next word or a word in the middle, and we end up with vector representations for words where the relationships between words are semantic. Anyway, the first poem. Walk like this. 5 seconds, guys. Okay, Pokemon Shedinja. What is the first statement true?
No, it's false.
Thank you. Pokemon Misdreavus. Misdreavus? Yang Wanjin. Is the second statement true? No. Pokemon Smoochum. Okay. Misdreavus, is the second statement true? No. Okay. Pokemon Smoochum, is the second statement true? True? Okay. And Pokemon Oddish, that's Rohit, is the third statement true?
Yes.
Thank you. And Skeptile, Pokemon Skeptile, is the fourth statement true?
False.
False. Okay. Let's see if they're right. The distance between any two non-identical one-hot vectors is the same. True, right? Words are represented as one-hot vectors rather than embeddings because these do not impose any a priori assumption about which words are closer than others. Word embeddings derived from language models are lower dimensional real valued representations where the distance between words is a meaningful representation of their closeness, but none of this helps you add a new word to your vocabulary. This is a problem, right? Because adding a new word to your vocabulary means you're going to have to increase the dimensionality of your space. And that's something that's not going to be feasible. So anyway, now let's go back and look at how we would actually use this to model language. Now, I want you to pay attention over here because this is something that's going to keep coming back. Here's your standard recurrent network. You're using a recurrent network. and the sequence of words goes in. At each time, the next word is predicted. And so you can train this just given text without the actual labels, right? That's because you're always predicting the next word. So if I just give you a sequence of words, W1 through W20, then after you see W1, the word to predict is W2. After you see W2, the word to predict is W3, right? And then after you see W3, the word to predict is W4. So at each point, the thing to predict is the very next word in the sequence. So just the input sequence is sufficient, right? Again, at the input, you would be projecting things down. And so you can just train the network to always predict the next word. And this means that you can use backpropagation to train all the parameters of the network, right? Now, I can use this model to also generate word sequences. And the way I would do this is I just feed in the first, say, few words in the sequence, or first few symbols. In this case, I've fed in 3. And after having fed in 3 words, the output is not a unique word. It's actually a probability distribution at each time, right? So it would compute a probability distribution for the 4th word in the sequence. And from this distribution, you can actually sample the 4th word. And that becomes the next word and the sequence, right? And now this is going to generate the probability distribution for the 5th word in the sequence. And from that, you can sample the next word, which goes in, and so on. And you can keep continuing, right? And when you keep continuing, eventually, when do you stop? There are situations where there's a natural termination. Like if I'm generating a C program. When my loop closes, when my when my open brace closes, my program is done. So I have ended. But in most cases, there is no natural termination. We actually have to indicate it. Here was a nice example from this one was, you see a lot of work with generating music with language models. This just uses a simple LSTM. Right? So I could play it for a few minutes, but this was a trivial LSTM trained to, please, I broke my regularization. Anyways, so with a few layers of LSTMs, and this was back in 2015, right, way back when. I like to put it out here just to show how much you can squeeze out of the most trivial forms of recurrent neural networks. All the fancy models that you see these days, they're just icing on the cake. These things do a fantastic job, right? So we can keep drawing samples. Even in the case of the music too, it just keeps drawing samples to generate the next line in the MIDI. That thing was using MIDI for pianos, right? When do we stop? To stop, we need a marker to actually indicate when things must end, because a sequence of words or symbols by itself does not indicate if it's a complete sentence or not. For example, if I said 4|8, it's unclear if this is the start of a sentence, the end of a sentence, or both, right? Similarly, so I'm going to put in a couple of tags. One is a start of sequence marker, the SOS. Literally indicates the start of a sentence or the start of a sequence. The other is an end of sentence or end of sequence marker, EOS. And so when I have things like this, if I just say 4|8 without any tags, it's neither the start of a sentence nor the end of a sentence. It's somewhere in the middle. But if I have an SOS 4|8, then clearly it begins with a start of sequence marker. So these are the first 4 words in my sentence. In the third case, I have 4|8 EOS, which means it ended after 8, because the next thing is an end of sequence marker. And so these are the last 4 words in the sequence. And then, of course, I can have SOS 4|8 EOS. And this is a complete sentence all by itself, because I started, the 4 words came out, and then the thing was terminated, right? And we can use some shortcuts. We might want to say that, I'm going to use the same symbol for both. Just give you an S symbol, which says something is either started or ended, and often, whether it's the start of a sequence or the end of a sequence is obvious from context, so that should be sufficient. But the point is you do want a tag which indicates when something began and when something ended. It may be explicit or implicit, but it is required. And so when I'm generating stuff using my language model, which has been learned to perform next word prediction, I can keep outputting words, basically computing probability distributions and drawing words from it. And I will do so until I actually end up generating an end of sequence marker, and that is when I get to stop. And so we have a port. Okay, time's up, guys. Pokemon head across. What's the answer? That's Caleb.
SOS, hello, EOS, the first one.
SOS, hello, EOS. That's the one. That's the only correct one over here, right? The rest of them are incomplete. Thank you. And so far, so good. So that was the detour. I'll stop right. I'll get back to the main path, which is we wanted to talk about sequence to sequence conversion. A sequence goes in and another sequence comes out, right? And specifically, we're looking at the second example where there may be no correspondence between the output and the input. The output may have the number of words in the output may have no direct relationship to the number of words in the input. There may be no order correspondence, nothing whatsoever. There's nothing about the output that actually can be explicitly, or there's no guarantee that there's anything in the output that can be explicitly identified with any component of the input. So the first one, the order correspondence is handled. We're going to be looking at the second one, right? That is this problem here. We've seen this network before, where an input goes in, you analyze the entire input, and back there, can you shut your laptop? Again, if you want to work on stuff, you can go outside and do it, finish it, and come back, right? This is the second time I warned you in class. Don't do it again. The next time I will ask you to leave. All right. So this is the kind of network we're speaking of, where an input sequence goes in, you analyze the entire input sequence, and once the input sequence is done, you generate the output sequence. So again, there's no need for correspondence anymore because the production of the output is unrelated to the consumption of the input. So it has two components. The first one, it processes the entire input to generate a hidden representation for the input. And the second one is that's my sticker is messy, right? Here's what a trivial piece of code, right? Pseudocode for it. You're processing the input sequentially left to right. At each point, you're generating the hidden representation, and for the next time step, you're using the latest hidden representation and the input to produce the updated hidden representation. And then when the entire input sequence is done, you're going to have just this hidden representation of the entire input. And then this is often what we call the encoder. It encodes the input into that hidden representation. And then the second component of the model is this guy here, which takes in that hidden representation and generates the output. So this, again, the first pseudocode, the first portion encoded the input. Now we're using the encoded input to generate outputs, right? At each time, now this is relevant. You start off with the initial hidden representation, and this is just a standard recurrent network. The recurrence is entirely through the hidden state, and the output is drawn is computed from this hidden state, and from that, the next word is drawn. So would this work? Or is there something potentially broken about this?
How does it know like how much more to generate?
You keep generating until you get the end of sequence marker, right? So here is what the situation is. The output at each time is actually a probability distribution from which we are drawing a word. Now, the problem with this is that when I generate a sequence of words, I have my X, this is my entire sequence going in. This is my H1, H2, H3, right? So these are my time is going down over here. And then from this, I have my output distributions being computed, Y1, Y2, and so on, right? So what is being computed is a probability distribution. The actual word we output is drawn from this distribution, right? So this, at this time, at time 2, we have no idea what we yanked out of this distribution, right? And so you have this situation. Each word that is output, the word that is output from here, I just sampled something from here and got word 1. I sampled something from here and got word 2. The sampling of word 1 has no bearing on the computation of Y2, right? So to give you an example, if I was trying to performing a machine translation task, right? And at the second time instant, I got a probability distribution, and I'm drawing a word from it. I could draw either a or an. Whether I drew a or an does not influence the probability distribution at the next time. So I could still go ahead and draw the word dark, regardless of whether the previous word sampled was a or an. But we know that dark does not follow an. Dark follows a, right? So how would we fix this problem? How would we ensure that at this time, if I sampled the word a over here, dark has high probability, whereas if I sample the word an, dark does not. So how would we make that happen? Anybody? I can feed this word back in here, right? And so that's the only way we can actually ensure that we have informed computation. And so you want to actually have the model self-reference. In other words, the way the process must work, you'd have the input, and the input is going to be some sequence of words or tokens, symbols, which begins with a start of sequence marker, which may be implicit, and ends with an end of sequence marker. And when the end of sequence marker is encountered, that corresponding hidden state is the one that we're interested in, right? And that stores all the information about the sequence. And then that's the first recurrent network. And subsequently, the second recurrent network uses the hidden activation that the first one computed, the little red square, to generate its outputs. And it's going to continue producing outputs until end of sequences drawn. So at the first time, you get some probability distribution, you draw a word from it. But now this goes back in, and then you draw the next word and the next word and then the next word and so on until the end of sequence is encountered. What does this look like? We've just seen a very similar process a few minutes ago. Does this look like language generation? Right? This is exactly language generation at this point. The only difference was that in the process of generating language, the initial hidden state was not, abstract and generic. That was drawn from processing the input. So the second portion of the network is literally a language model, which takes some hidden information from its initial hidden state, from what the input, whatever was the outcome of processing the input. And observe that in this process, because it's the process of generating language. Each word, the probability distribution you compute at each time depends on the word that you do, not just to the previous time, but the entire sequence, because the whole thing is being fed back in, right? Now, I've drawn a very simple model in all of my examples with just this one layer for the hidden state. Do not be fooled that the little sequence of green boxes can be arbitrarily complex. It could be 2 layers, it could be 200, it could be anything, right? Again, how we actually design our hidden states is up to us. The high level stuff is all we're looking at. Okay. So pseudocode, I'll skip it. Now, again, going back, the terminology, the portion that processes the input is what we will call our encoder. And the structure that it generates a hidden representation from the input. And the structure that uses this hidden representation to generate the output is what we will call the decoder, right? Now, this is what I call a simple translation model. So I can use this network literally to translate from English to German. The English would go in, and then when the English sentence is completed, you're going to get a hidden representation for the English sentence. I can use that to go ahead and generate my German sentence, right? I know my English sentence is completed when I see the end of sequence marker. And that, so here is my pointer.
Oh, it's like behind the back.
Aha, okay. Too many things out here. But so once my end of sequence marker is encountered, I get my hidden representation. And that has to trigger my language generation, right? But the language generation always begins with an initial word. So the initial word is going to be my start of sequence marker. At the very first time, I'm saying, here's where I start my sequence. Begin producing words. And then I can go ahead and continue producing words till the end of sequence marker is generated, right? So again, observe that we are not at this input. We are not actually going to be feeding in one-hot representations for words. We would actually be feeding in the embeddings, which means there's a projection matrix immediately after the word. And in the case of language translation, the projection matrix, I mean, the vocabulary for English and German are very different, right? So very likely the projection matrices are going to be very different for the two. The one-hot representations are going to be very different for the two. You may have different projection matrices on both sides and any kind of combination, right? But we won't focus on that too much. The point to note is that anytime I draw a picture with a word going in, you must immediately assume that that word is being projected down to its embedding through some kind of a projection matrix, okay? So now let's go and take a look at what the network actually produces. The network at any time, again, this is a language generation task, right? At any time, the network is producing a probability distribution, but specifically, what is this probability distribution? That probability distribution is the probability for a distribution for the next word given something. What's given at that point? What was given from the outside? Given is what you have provided, right?
The start of sequence.
It's going to be the input word sequence, right? So this would be the probability distribution for the first word in the German language, in the German sentence, given the English sentence, I ate an apple, and the start of sequence marker. So that very first probability distribution is P of, the probability for the distribution for the first word, given the entire input and the start of sequence marker. Now from that, you would be drawing a word. You're basically drawing a word from this distribution, which goes back in at the next time. And now it computes yet another probability distribution. What is this probability distribution?
Everything up until now, including the first generation.
So this would be the probability distribution for the second word in the output, given the entire input sequence and the start of sequence marker and the first word generated. Ish in my example, yes, Jacob.
Would the first
So it could be outputting probability distributions, but we're ignoring those, right? We're not using those. Yeah.
Is the second decoder learning the Russian versus German vocabulary?
So the vocabulary is specified, right? You have to say this. Yeah, the vocabulary is it's computing a probability distribution over some n symbols n plus one, which are the vocabulary.
Like very different. So how's the representation from English?
So it's not. They're very different. So that's the second component is a language model for German. That's it.
Oh,
Right? That's what I mean, that's something I should emphasize. The decoder is its own entity. All it's doing is getting some information, some vector, something from the encoder, but then it does its own job, right? So the only connection to the encoder is through the information that's being passed in that has been obtained after processing the input. So this second term, yeah.
So you talked about like the memory of the given input and how long it kind of lasts. Is there a similar idea here?
So that thing, whatever, say the entire input has been processed, something has been generated, right? That's it. So this probability distribution is the probability for the second word given all of this and these two. That's about it. Yeah.
Verify like the difference between this and the language generation we were talking about earlier.
So in the language generation, what was missing?
Start and end. I don't know.
In the language generation example, the only thing missing was this guy. So, right? So this is exactly language generation with an extra component, which is this information drawn from the input sequence that has been fed in. This is exactly the same as language generation, right? So if you look at the equation over here, in the case of language generation, you'd be given P of OK equals W, given OK, O1 through OK minus 1, and this portion would be missing. Here, all that happened is that on the given side, you also included the input sequence. Did that answer your question? Yeah.
how are we like pulling the German words from their English representation?
You're not. This is just a language model.
Because isn't the hidden the part that's going into the decoder? Isn't that the activation from the English side?
It's a vector. That's it, right? It could be anything. So just think about this.
Are you feeding like both vocabularies into the encoder?
So now here, just think of my German language generator, right? So my German language generator is doing something of this kind. At each time, it's generating words, and this goes in. That's my German language generator, right? And there is an initial hidden state. That's your RNN. Is this referring to English, the German language model?
And that's the German.
That is the German language model, right? All I'm doing is that initial hidden state happens to have been computed by my English encoder. So the two do not talk. They do not need to communicate in any other manner. Chetan, you had a question?
Yeah, I think you kind of just answered it. So like if you wanted to have like a different language, the only difference would be you changed the key.
If I wanted a different language generated, I just change the decoder. So if I want to go from English to Croatian, right? I just change the decoder. If I want to go from French to German, I just change the encoder.
And like just as how before we had like learned the initial hidden state, here we just use the encoder to get our hidden state.
The encoder is giving us our initial hidden state. That's about it, right? So very simple. And it's amazing what this can do, right? And so at each point, you're getting the word probability distribution for the next word, and you are drawing a word from it. But at each point, the probability distribution is the probability of the word given the entire input and all the words generated until that time, because those words are going back into the decoder, right? So, and we can keep doing this till we get to the end. So at each time, the network produces a probability distribution over words given the entire input on the encoder side and all the words until the current word, right? And the next word is drawn from this distribution, which is provided as the input to the next time. And this process continues until an end of sequence marker is produced. Now, so that's just my pseudocode for what we are doing. You'd have an encoder. The encoder is going to produce a final hidden state H, which goes into my decoder as the initial hidden state. It may be transformed in some manner because the two hidden states are of different sizes. I could use a matrix to change the size from the larger size to the smaller size of this, right? Or vice versa. And now that goes in here. At each time, the recurrent network is taking in the hidden state from the previous time and the word output at the previous time to generate the latest hidden state and the probability distribution over words. And the next word is drawn from this probability distribution over words, right? I've used this term drawn from very casually. What exactly do I mean by drawn from? Now this ends up being important. So if I've drawn an entire sequence of words, O1 through On, right? What is the probability distribution for that sequence of words that I have drawn? O1, O2, O3, O4, O5, end of sequence. So that is the probability distribution for the specific sequence of words given the input. So input, I ate an apple, right? And here I've drawn whatever, Shaba and an apfel gegessen, okay? And end of sequence marker. What is the probability of having generated this particular sequence of words given this one? P of O1 through OL given I1 through IN. I can break that down using Bayes' rule, right? It's going to be P of O1 given the input times P of O2 given O1 and the input times P of O3 given O1, O2 and the input. What is that? That's simply, so what are each of these probabilities? These are just the terms that I have computed from, these are just the probabilities assigned to those symbols by the network, right? So the first term over here, so when I generate a sequence of words, like so, I could just read those probabilities off from these probability tables, right? And if I multiply that sequence of probabilities, that's going to give me the probability of the specific sequence of words that I drew given the input. That makes sense to all of you guys? Makes sense, right? So the probability of the word sequence that I drew is simply the product of the probabilities computed for each of the words in the sequence as the network operated left to right, okay? Now, if you're performing machine translation and I give you the word sequence, I ate an apple, which word sequence would you want to generate? Mm-hmm. Yeah, but what would that be in probability terms?
The most likely.
The most probable sequence is what you want to generate, right? So what we really want to do is to produce the most likely sequence given the input, which means that our draw process must be something that generates the most likely sequence of words. And here's where things get a little complicated, right? I want to draw the sequence of words O1 through OL such that the product of the y's for each of the words is maximum. And the complication that arises here is that any word that is drawn influences the next y, right? So how do we draw the words at each time to get the most likely word sequence? Here's a greedy answer. For the first word, I just pick the most likely word. Feed that back in, then I get the next probability distribution, I pick the most likely word. I can keep doing that, right? Would that work? I see you nodding very enthusiastically. Would it work?
No, it won't work.
Why would it not?
Sometimes like you start really bad, hoping this really bad result. In the end, it won't happen.
So I think she's saying what I'm going to say right now. But yeah. So if I just chose at each time, if my draw was simply picking the most likely symbol y, this is greedy, and you can run into problems. Why so? Here's an example, hypothetical, right? And let's say that I was doing something like speech recognition. So, I'm looking at acoustically confusable words. Let's assume the first word I chose was the, right? And for the next word, I have two choices, the word nose, which is this object on my face, and the word nose with a K, where the K is not actually pronounced, right? And just hypothetically, assume that the word nose, this thing on my face, is marginally more probable than the nose. If I just chose the nose, right, then what is the next, or let's say the first word is he rather than the, okay? So the first word I've chosen is he, and for the second one, the nose on my face was a little more probable than the word nose, and I chose nose. What word can follow he knows? Is there any word that distinctly follows he knows? There aren't, right? It's a really bad sequence of words. And so a language model which is halfway decent is going to be very confused about what follows. It's going to assign low probability to pretty much everything, right? On the other hand, although the word nose was marginally less probable than the nose on my face, if I had chosen nose, right? He knows is a very reasonable linguistic structure. And so the subsequent word, there are many plausible subsequent words, and depending on whatever the speech was, you might actually pick a word which has very high probability, right? And so now you have this thing where although the second word chosen was less probable in the second case, this resulted in a much greater probability for the third word. And so when you multiply the probabilities of the three words, the second case ended up with a higher overall probability than the first case, even though you chose the more probable word in the second position, right? That makes sense? Right. So you cannot be greedy. If you're greedy, this is likely to cause confusions downstream, which make the overall hypothesis much less plausible. And the problem here is it's impossible to know a priori which word leads to the more promising future. I just gave you a very simple trivial example over here, but in reality, we didn't know whether I just gave you two, nose and nose. In the more generic situation, you wouldn't know, right? And in fact, I chose the second time instant over here, the second word as the cause of my confusion. But then if I take a step back and look at the very first word, let's just assume the word the and he, or the and he, were very similar in probability. And he was marginally more probable, so I chose he. But if I had chosen the, then I could well have chosen nose, the nose on my face, and the nose has a lot more structure to it, right? And could have produced something even more plausible. So anytime you take a guess, if you make a wrong guess, you could be committing yourself to a poor future, right? So we've encountered this problem before. How would you deal with this? Beam search, right? You don't commit. So what you would do is something like this, right? One alternate option is just randomly draw a word at each time. It turns out that if you randomly choose words, as opposed to being greedy, very often the randomly chosen sequence of words will actually end up being more likely than the greedy solution, because words influence other words downstream. Again, there's no guarantee that it's going to give you the most likely word sequence, but still, right? So over here, I could have just said randomly sample from y of t. And it turns out this does a pretty good job of predicting the word sequence. But if you want to be more optimal, then we want to do something a little more careful. But here's the poll first.
What's the answers?
Okay, guys, you haven't seen the answers. Right. If you're confused as to how many questions there are in the poll, take a look at the owl. It has as many eyes as the questions. changed. Why does it do so? Time's up, guys. And you got a freebie too. You got the answers. Pokemon Meganium. What's the answer to the first one?
True.
True. Okay. Pokemon Seal. True. And Pokemon Spearow. That's Yunjin Na. What's the answer to the third one? Pokemon Spearow? Absent. Pokemon Nidoqueen? False. Thank you. Okay. So true, true, and false, right? For greedy decoding, we choose the word that has been assigned the highest probability at each time. True. In decoding through random sampling, we randomly choose the next word according to the probability assigned to it. Also true. The procedure used for randomly sampling has been presented in today's class. I haven't actually showed you how to randomly sample from a distribution, right? I'm assuming that all of you know. If you don't, post on Piazza, I will give you the answer, right? Here's our problem. Our choices can get us stuck. Making a poor choice at any time commits us to a poor future, but we cannot know at that time if the choice was poor. So solution, we don't choose. Here's what you do. At the very first time, you give it a start of sequence marker. It's going to assign a probability to every word, right? So it's assigned once you've assigned a probability to every word, in principle, you could be using every one of these words to initiate the decoding. But if you did that, this is quickly going to blow up. So what we would do is, and then we could just keep going downstream, right? But then if we did that, this is going to blow up. Over t time steps, if you have a vocabulary of size v, this tree is going to become v raised to t large. So instead, at each time, we are only going to keep the top k scoring forks. K is your beam width, right? Now, you don't actually have to expand things out and then prune. You can decide which ones to keep based only on the probabilities of these words at this time. So you can just keep the top the top k most probable words, and then make those many copies of the decoder and pass those keywords in, right? Each of those keywords in. And so now, the output word sequence over here has a probability which is, in this case, P of the and P of he, right? And these ones would be expanded out. And then from this expansion, now we can just keep the top k, right? But here's the key thing. Again, you can do the pruning before you actually compose the network. But anyway, the key thing is here. The decision of which k to keep is going to be based on the entire path sequence and not just on the probabilities assigned to the latest word. Because you want to pick the most likely sequence, right? So the fact that we're going to be using retaining nose and nose is based on the fact that the probability of v times the probability of nose and the probability of he times the probability of nose, these two are the highest. The sequence of probabilities is what you're going to be using to decide which ones to keep, right? So at each time, the actual pruning is based on the product term over here. And so then you retain the top k, expand them out, and then each one of those, in this case 2v expansions, has its own unique sequence probability, which is the product of all the probabilities until that location. And you just retain the top two and keep doing this, right? This process makes sense, right? And the fact that you're actually using the entire path probability to decide which ones to keep. And then when would you stop? Can you say that aloud? We can keep doing this, but it's not enough to find an end of sequence marker. Why? Because you might find that although this came up with the end of sequence marker, this is still more probable, right? So you're going to keep going until the most probable sequence is terminated with an end of sequence marker, right? And the thing is, once you get an end of sequence marker, that path can no longer be extended. So you'd be extending the remaining paths, right? And you'd continue till there's still the most probable sequence that ended up had an end of sequence marker. And you could keep doing this to generate more than one sequence if you want. Okay, time's up, guys. Pokemon Mankey, Dia Dinesh. What's the answer to the first one?
True.
True. And Pokemon Pidgey. That's Malachi. What's the answer to the second one? Pokemon Pidgey.
I think it's true.
It's true. Okay. So theoretically correct decoding requires you to evaluate the entire tree, representing every possible word sequence. Beam search is not theoretically correct, right? Because you're pruning things. It must be false. So you're likely to lose the most probable sequence when you do so. Yeah.
Good question. On the previous slide with the trees, my question is like, will this already prioritize like shorter sentences and longer because the probability of shorter sentences will be different?
Yes, it will. So we're going to have to throw in some heuristics to deal with that. You're absolutely right. Yeah.
And also, would it ever make sense to vary the K that you keep, so like keep more earlier on?
Yeah, you can try, yeah, it does. It makes sense to try those things, right? It will eventually depend on your computational resources too. So how about training the system? Now this is where something interesting, the divergence between language models and sequence to sequence models comes in. There are two ways to view this problem of training. One way to view it is to say that I'm just training a language model which has been seeded by an encoder, right? In which case, your input is going to be the input sequence. Your training data are going to comprise the input sequence and the corresponding output sequence. And at each time, you could just be feeding in the output sequence and predicting the next word and following that chain. And so that's going to be your training, right? So what you would do is this. If I had I ate an apple and ich habe einen Apfel gegessen, then you give it I ate an apple and it generated the red node, right? And then you would be you'd be feeding in ich habe einen Apfel, and after ich the predicted word would be habe, after habe the predicted would be Apfel, and so on. And so this is treating it as a language model seeded by an encoder, right? But if I think of it as an end-to-end system, that doesn't really work all that well. Why so? Because in an end-to-end system, we have to think of it slightly differently, right? In an end-to-end system, the way we have trained networks so far is that here you had your network, your input went in, you generated an output, and you compared it with your desired output. This is how we computed our loss, right? If we were doing things in this manner, what would the equivalent over here be?
The input would be the English sentence, and then the output would be the German sentence, and then.
Exactly. All you could do is the input sentence, and the output is going to be the German sentence. What would the problem with that situation be? The loss. Go ahead. There was an answer on Zoom. There is no guarantee that the output is going to have any correspondence with the input, right? Especially in the initial portion of the training, you might just say, I ate an apple, and the output could be a 200-word sequence of blah, blah, blah. How are you going to compare it to Ich habe einen Apfel gegessen? You cannot, right? And so you end up with this horrible situation where if you just use your conventional training, which is the correct thing to be doing, right? this is what you must be doing, you cannot train. And so we fall back to our time-tested strategy, where we treat it as a combination of a language model and a seeding model, right? So the distinction between the two makes sense, because this is going to come back when you're doing your homeworks, right? And so your standard training, you'd have a forward pass. If you treat it as a combination of an encoder and a language model, you pass the data in, and then you make your predictions, compute your divergences as before, and then you can back propagate things. And for this simple translation system, there were several tricks that went in. For instance, for each training sentence, they would pick only one random word from the output and only back propagate that divergence. Or they would find that one of the problems is, again, you're given training instances where you have an input sequence and the target output sequence, and that's what you're going to be training with, right? Another standard trick that they applied was that they would reverse the order of words in the input. Why? And this ends up being influential, because if I did this the conventional way, by the time I got to the end of the sentence, I ate an apple, I've forgotten all about the I. And so the initial portion gets diluted down, especially if the input sentence is very long. And so they found that if you reverse the sequence like so, then it does a pretty good job of cottoning onto the initial words. And then because the initial words have such strong conditioning, the subsequent conversion is much more effective, right? And you can use the same tricks as before. The other one was, and even the simple tool has many applications, like machine translation, ASR, dialogue, image to text. Here are some examples. Before we see some examples, how well does that final state actually capture the input? Now the final state, the final hidden state, is just a vector which is representing the entire input sequence, right? It turns out that even that does an amazing job of representing the entire input sequence. So here, for example, they're showing you two-dimensional PCA projections. Uh-oh, come on. Yeah. Mary admires John, Mary's in love with John, Mary respects John, right? John admires Mary, John is in love with Mary, John respects Mary. They are the three sentences. They all have the same semantic structure, except you've flipped Mary and John, right? And observe that the three are arranged in pretty much the same shape, right? Or here, I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. You're just changing the, the manner in which it's said, right? If you flip the subject and object, it's semantically still the same. So you find that the shapes end up being the same. So that's that final hidden state actually ends up capturing structure. Yeah.
What purpose is flipping the input sequence exactly?
So because you're depending on the fact that if you did this the regular way, by the time you got to apple, I is almost forgotten. When you flip it, you're sort of latching onto the I much more strongly, and because conditioning on the initial value is strong.
But then won't apple be forgotten?
You're conditioning, right? It's left to right. So it ends up being doing a better job. We'll deal with this in the next class, right? And even the simple model has some very nice examples. Here is an example from machine translation. Yeah.
I was wondering, like, if we're back propagating the loss through the encoder, then isn't the encoder designed to work with a specific encoder? How can we swap it out between like English and German and English and French?
You're right, and I would have to fine tune, right? But the structure is going to be the same, right? In general, you can come up with other kinds of tricks where you train across all kinds of combinations and learn something generic, right? So these were machine translation examples. This one was one I found most impressive, dialogue. The machine says, what is the error you're running, please? And the human says, I'm seeing an error related to VPN. And the machine says, what is the error message that you're getting when connecting to VPN using Network Connect? Connection refused or something like that. May I know the version of the Network Connect you have? I'm not sure I know that. Is the Network Connect prompting for any user certificate? This is a completely automated dialogue system, right? And just uses the very simple network architecture that we just saw. It's been trained on this data. And you can use this for image captioning. Once you think of it as language model with an initial hidden state. That initial hidden state could come from analyzing an image, right? You have a standard CNN for analyzing the image, and then you do the language generation, you can train your model, and you get these very cool, very early image captioning examples. Pretty amazing, right? And they did this for videos and such like as well. I'll stop here. The issue here is that we're overloading that one guy, right? The simple model kind of works really well, but only for short inputs. How do we generalize for larger inputs? We'll deal with that in the next class, guys. Okay, here's your chance. Come on up. We'll take a picture. Come on. Yes. There you go, right?